Okay, number 3. A robot probe drops a camera off the rim if let me get my black pen. 24-kilometer deep crater on Mars where the free fall acceleration is negative 3.7 meters per second squared. Find the time required for the camera to reach the crater floor and the velocity with which it hits. So we are looking for time. I'm going to circle that. That is our t. And the velocity with which it hits. So that will be our final velocity. Okay, so as I have been doing, step 1 is always draw a picture. So we have a crater, and it's not going to be a fancy crater, and that's okay. So we have a camera that is going to do a free fall. It's going down, and the crater is 24 kilometers deep. We'll put that there. And we have a acceleration that is obviously going downwards. It's the gravity. But one thing about this negative does not mean that it's like slowing down or anything. It just means that it just tells us the direction of the acceleration. We know that gravity usually goes down to the floor, to the ground. So that tells me that in this problem, if going down is negative, the direction is going to be negative, then going up would be the positive direction. Now, sometimes the problem will indicate that to you, or sometimes you have to decide on your own whether or not you want to make up the positive or down the positive. Usually it's, if it's going up, it's positive. So just keep that in mind. So how is our camera going to move? It's pretty obvious. It's going to come down here, and it's going to have a velocity. I'm going to call this starting point state A and the ending point state B. So what do we know about state A? There's, oh no, I'm sorry. Okay. We can assign a velocity at state A, but maybe you can tell, but this initial velocity at state A is going to be 0, right? Because it's a free fall, it's just falling down. When you drop a ball, like just imagine you dropping a ball, that moment that you, right before or right when you drop it, it's starting with no velocity. So VA is going to be 0, but we obviously will have a VB, which will not be 0, right? Because it fell down and now it's moving with a velocity caused by the acceleration going downward. So another thing that we should write is that we don't know how long it took, t, and we are asked to find t and VB, right? So I think that's good enough for now. Now I will go on to step 2, which would be identifying our oops. Oh man, sorry. Step 2 would be identifying our knowns and unknowns. What do we know about this problem? We know a little bit. First thing, we know that the distance this camera traveled is 24 kilometers, but be careful about kilometers. Oh no. Sorry. I think I'm pressing a button somewhere. Okay. The distance that the camera travels is 24 kilometers, We usually do not use kilometers in this problem, as you can see. For example, the acceleration is in meters per second squared. It's not in kilometers per second squared. So I want to change this to meters. And that's unit conversion should be pretty simple, I hope. So we want to get rid of kilometers. So the denominator is going to be 1 kilometer, and 1 kilometer is, we want it in meters. So 1 kilometer is 1,000 meters, which tells us that the kilometer will cancel out. So it would be 24 times 1,000 meters, which would be 24,000 meters, which is, I don't know how much you guys like can feel what a meter is, but that's like, that's a long way. What else do we know? We know VA is 0, right? Because we're starting from no velocity, no speed. We know what our acceleration is. Oops. Acceleration, it was told in our problem, it was negative 3.7 meters per second squared. What else? Is that it? That might be it. Okay, now our unknowns. It will be, we do not know how long it took for the camera to go from state A to state B. We also don't know the velocity when it's at state B. Yeah, let's go with that. Now step 3. Step 3 would be identifying which equations that would be relevant to our problem. So, oh man, our first equation, which you can look at your equation sheet, it's going to be V final equals V initial plus AT. In our case, the final velocity would be VB, right? That is the final state that we are at. VI, the initial velocity would be VA, right? I hope that's clear. Distance would be the initial velocity, or how long it took, how long we traveled with this initial velocity, plus half of the acceleration in time squared. Oh, that will be, the first one is number 1, this is number 2, and oh my god, wow. Okay, the last one will be V final squared minus V initial squared equals 2AX. That is going to be our third equation. And we're going to be referring back to these constantly when we solve our problem. So step 4 would be to solve. We are asked to find 2 things right here. You want to look for t first, how long it took from our camera to go from state A to state B. So I'm going to look at our equations and see which one I want to use. I immediately know I do not want to look at number 3 because it doesn't even include time in it. I can't use number 3. Let me look at number 1. V final, that's the velocity at state B, right? Do we know that? No, we don't know that. And we also don't know the time. That's what we're looking for. If we're looking for time and we don't know another variable in that equation, we can't solve for t because we don't know what VF is. So I don't think we can use equation number 1. I'm going to look at number 2. The distance that we traveled, we do know that, right? We go from right here to here, it was 24 kilometers. V initial, that would be the initial velocity at VA. We do know that, right? Because that's 0. And t, that's what we're looking for. Half A, acceleration. We do know the acceleration. It was given to us, right? Of negative 3.7 and t squared. That's what we're solving for. So I think we can use number 2. So I'm going to rewrite that here. Oh my god. The distance that we travel is equal to the initial velocity. In our story, we call that VA, right? So VAT plus half of the acceleration and how much time we traveled. I am now going to put in my variables. The distance we traveled, it's not 24,000. Oh man, oh, I forgot to explain this part. Sorry. So, whoopsie. It is not 24 kilometers that we traveled, because if we 24 kilometers, that is a positive number, which would mean that we moved up. But we didn't move up, we went down. So this x, 24 kilometers, the distance we traveled, needs to be negative 24,000. The negative indicates that we went downward. So oopsie for forgetting that. I'm glad I caught that right now. So I'll include that. It's going to be negative 24,000 equals VA, the initial velocity. That was 0, right? And T, that's what we're looking for, plus half of acceleration. We do know that, and it's negative, right? Because it's going downward. Negative 3.7 T squared. So now it's just going to be algebra of solving and manipulating to find T. I'm going to rewrite this, and I'm going to get rid of this because it's multiplied by 0, so it's going to be 0. I'm going to rewrite that. 24,000 equals 0 plus half of 3.7. That would be 1.35, I think. I hope that's right. It'd be negative, right? Negative 1.35 T squared. I'm going to fix this. So it'd be negative 24,000 equals negative 1.35 T squared. Now, just a little tip that I use is that I do not like to calculate stuff. I don't want to put things in my calculator until the very, very end that I have to. So in that sense, this was a bad example. I should have not calculated this, but whatever. So I want to divide both sides by negative 1.35, right? But I'm not going to put that in my calculator just yet. I'm just going to still keep it a fraction, because thankfully the calculators that we use, we can put in fractions and they'll do it for us. So we have that. And now we want to take the square root of both sides, right, to get rid of that squared. So I'm just going to flip it. So it's like t equals, and then the square root of 24,000 all over 1.35. And now you should put that in the calculator because they can handle that. And the answer should be, oh man, sorry, I think I made a mistake. It's not 3, it's not 1.35. Oh man, so sorry. This is 8.5. Forgive me, please. Sorry. It was 1.85. Oops. Sorry. So if you put that into the calculator, put that in, it'd be like something like 113.8. The answer said 114, so I'm assuming we're just going to round that up. And that is our time of how long it took for our camera to go from state A to state B. We also have to find the velocity when it hits the ground, VB, our final velocity, right? So I'm going to look at our equations. I know that we are not going to be looking at one of them. It's going to be the second one that we're not going to look at. V final, that's not in here. So we can't find V final with this. I'm not going to look at that. I'm going to look at number 1 first. V final, VB, that's what we're looking for. V initial, the VA, right? We do know that. That was 0. Acceleration, we do know that. That was negative 3.7. And time, we didn't know that at first, but we just solved for that, right? We just solved how long it takes to go from VA to VB. That was 114 seconds. So I think we can use number 1. I will rewrite the equation. In our problem, we didn't call this V final, we called it VO. Oh man, that can't be good. VB equals VA, the initial velocity, plus the acceleration, and how long we traveled for. VA was 0, right? Acceleration was negative 3.7 because it's going down, and my pen is dying. Time. We traveled for 114 seconds. Oh my gosh, can you just put this in the calculator? And it should be something like negative 400 and oh, that's bad. Negative 421 meters per second. I hope the negative makes sense because it's going down. When you solve with these equations, the signs that you get should correlate correctly with the problem. So if you got like a positive right here, but we obviously know that it's not going upward, it's going downward, I would recheck your work to see if maybe you made a mistake somewhere. And that's it. How do I stop this? Oh man. Okay, there we go.